Okay, thank you, Laurent. And first, I want to thank the organizing committee for giving me the opportunity to present this work. It started some 5 years ago with all the collaborators that you can see here. So some of them are part of the past project, this project, the Ice Waveguide project that is now over, and there's another one starting this year. So what are we going to talk about? So first I'll give some context and state of the art about how we monitor sea ice. And then I'll present an experiment that we made in Svalbard. And the first part is going to be about the seismic noise and what we can do with it there. And then there's another part on icequake analysis, because we can do a lot with icequakes. And in a third part, which is going to be much shorter, I'm going to introduce some ongoing and future work, which I find quite exciting. So yeah, let's get straight into it. So the context, you all know this context. There is this alarming sea ice decline, and sea ice is an essential element of climate regulation. And what I learned also recently is that it's the first order parameter that's controlling phytoplankton primary production. So phytoplankton are being created under sea ice, and so it's important to understand how they are being created, and so sea ice is highly involved in that. Sea ice declines faster than anticipated. So prior to 2007, the GIEC predicted the seasonally ice-free Arctic anywhere from 200 to 2,100 years. So it was quite a long. It seemed like a long time to wait before it happens. And in 2007, this was updated, and it could happen as early as 2050. And then during my project, when it just started, there was a new update that said that it could happen as early as 2030. So what to take out of it is that sea ice model failed to capture ice physics and response to geophysical forcing. And this is because we are lacking field data to understand these rapidly evolving dynamics of the sea ice. So for example, we have some rough idea of its average thickness over the Arctic basin. So here I'm talking about the Arctic sea ice, by the way. Its density, its rigidity, its porosity, all are parameters that need to be included in sea ice models, which are also included in climate models. Also the cracking thresholds in the marginal ice zone, where the waves interact with interact and break up the ice cover. So yeah, you see here the trend of this year. We are following about the worst year that we had was 2012, where we reached this minimum. But on average, in 40 years, we lost about 40% of the sea ice extent. So how do we monitor sea ice? Generally, well, the most common method and the easiest one is to use satellite radar-based estimation of the ice thickness. So basically, you measure some reflection. You can estimate, if you are lucky, the snow thickness, the ice, the part of the ice that is the freeboard, and from that you can deduce how much is the ice thickness. But this is subject to high uncertainties on the density of the snow, on the thickness of the snow, on the density of the ice, etc., on the ice swell, etc. There's also some ice profiling sonar, which provides good accuracy on the ice thickness, but it's quite rare and not easy to obtain. You can imagine that driving an ice profiling sonar, going there, it's not very convenient. So the data are accurate but rare. And then there is seismology, which can provide not only estimates of the ice thickness, but also its elastic properties. And with very good accuracy, we're going to see that. some 15 years ago, the logistics for data acquisition with the classical methods, that is active methods, were too complicated. It required active sources, like I just said, and we had non-autonomous, or it was just the beginning of autonomous geophones. So we needed human presence in the field, and so that was associated with heavy logistics in some environment which is dangerous. So, but the rapid technological advances and methodological progresses with the era of passive seismology have led to a reconsideration of seismic methods. So a quick overview of what seismology has made for sea ice monitoring. So in the 50s, we had the first seismic experiments on sea ice. So it was, like I said, you had a few seismometers and heavy logistics to perform your experiments. So this is why they are quite rare, actually. In the 90s, I can isolate like 3 or 5 of them. So these are the main contribution where we started to get dispersion curves, inversion of these dispersion curves. So that's about it. In the 50s and the 90s, this is how much we have. And now, since the 2010, with the era of passive seismology, there is a regain of reconsideration of seismic methods. Started with David Marsan, who made the first noise interferometry with gravity waves on sea ice. And this is about the time where I was recruited at ISTER, and we had started to have discussions about what we could do. And this is how the project all started. So yeah, some contributions by me and other authors that's starting to get interest into that. So what kind of wave do we observe in sea ice? They are quite similar to the LAMB waves, but the actual LAMB waves that we have in a free plate. By actual, I mean the one that are most famous, I should say. So here I'm going to give the frequency wave number representation of the LAMB waves, because it's the easiest way to understand that it's multimodal. We see plenty of different types of modes with cutoff frequencies at the higher frequencies and stuff. So they all produce different kind of motion that can be useful to characterize, especially in non-destructive testings, the medium. But what happens when this is an ice layer resting on water? Then at the interface between solid and liquid, you have short waves. So you can expect to have an extra type of wave occurring. Actually, short wave are for 2 infinite media, but here we have an infinite, pseudo-infinite medium, which is water, but also a finite thickness ice. So this is why we call that quasi-short, quasi-short. And all the other modes have their branches that are slightly modified as well. Well, not slightly, actually. And so we call that quasi-LAMB mode. And here we're going to focus to the very low frequency range, which is the kind of range when we translate it to the global scale. The low frequency range where we have only 3 types of modes. So let me zoom into that. Here we have the quasi S0 mode. When you go to higher frequency, this mode starts to be dispersive here because there is non-linear relationship between frequency and wave number. But at these low frequencies, it's not dispersive. You also have a guided SH0 mode, which is similar. Well, the most similarity you can find would be the love wave. And this mode here, the quasi A0 mode, I'm not going to talk much about it because in sea ice it's so strong leakage in the water that you can't measure it at those frequencies. But the one here, the quasi-short mode, this one, which we is with this one that we are going to use much. So actually, the low frequency approximation of these modes is the actual wave, the shear horizontal wave, and the flexural wave here, which is common with the quasi-short mode. And here I'm showing the kind of displacement that they produce while propagating. This is flexure motion, okay? And here this is traction compression motion for the quasi S0 mode. So having that in mind, we designed a seismic experiment, and we went straight to Svalbard. So we landed in Longyearbyen, and we had to drive all the way to this part of the island, which is called the Van Miechen Fjord. And we zoom onto this area, which is the area. So we have a little town where we could rest here. Not a town, there was like 50 people, the miners. So we drill holes and install this array here. So I'm going to zoom on the array. You'll see that on the next slide. So we drilled like 250 holes to install Z-lamp nodes. Yeah. So we buried them about half their thickness and put back snow on that to insulate and protect the battery, prolong the battery life. And this is the drone view of the array. We also perform ground penetrating radar, just to confirm our inversions later. And some active sources. So we had a vibrating source, and also some improvised kind of source where we jumped straight onto the ice. And here we have Pierre Boué, who's done that perfectly. Right. So here is the situation: Svalbard map, the Van Miechen Fjord, which is here. A zoom on the Van Miechen Fjord here, and there is this moraine here what protects, kind of isolate sea ice from the rest. But we still have tides, winds and everything that we have on open sea ice. So this is our array. So we have 3 component stations in blue and 1 component station in red. The spacing is about 4 meters for the one component station, and 1 meter. We wanted really to have a high resolution. So yeah, here is our situation. We also used some remote small antennas to play the role as virtual sources with noise correlations. So this was our experiment. We left that to record for a month, March month in 2019. And here's what we obtained. So seismic noise. This is a zoom on the seismic noise. We had some noise. We had some many impulsive events, and also some transients here. So at all scales, we had some useful signals. These are the 3 components of the signal, by the way. And those data are available on the RESIF website. So if we look at the spectrum of this data, we see that we have some energy up to, I would say, 50 hertz in the noise, with plenty of spikes with the impulsive sources that have energy at much higher frequency. And also the field work, when we were there working. Here we were, we woke up maybe a bit late because we started at 8:30, but anyway. So this noise, we obviously, like a good apprentice seismologist, because I was in the field of ultrasound before, I said, okay, let's do beamforming and see how sources are distributed. And we can see that they are pretty isotropically distributed at all frequencies. Apart maybe here, the high frequencies do not propagate very much up to the array, because when you look to the south here, there was starting to be far away the shores where the icequake could happen. So it was an ideal situation, this isotropic distribution of sources, to calculate the noise correlation function. But before we move to that, I'll just show you a recording of an icequake propagating through the array. This is kind of top view of the vertical displacement. We see characteristic of guided waves here, which has much dispersion. But contrary to Rayleigh waves, it's not the low frequency arriving first, it's the high frequency. So because the mechanism of dispersion for guided waves is not the same that for Rayleigh waves. For Rayleigh waves, in an isotropic medium, they would not be dispersive at all. Why we have dispersion is because of the gradient of velocity. And this is some kind of material-induced dispersion. Here, the dispersion is due to the not a gradient of properties, but to the geometrical nature of the waveguide. Because, you know, the wave, they interfere constructively, destructively, differently at different frequencies. And this is why you get this kind of dispersion with high frequencies arriving first and low frequencies arriving later. Sure. No, it's not. I mean, there can be a coupling, you know, if you don't have a lot of thickness in the water. But so that would modify, you know, the coupling, and so the short it would be a different kind of short wave as well. So yeah. But in that case, here we have, given the frequencies we are considering, and given the water, it was 20 meters deep, there was no interaction. Right. So noise correlation function. I talked about virtual source here. So the geophones that we put here, we recorded noise here, and we correlated with the stations of the array, starting here with the one at the center of the array. So what we did also was to jump here, just at this station. It gave us the waveform in blue. Okay, and here we have the noise recorded here, the noise here recorded at the other station, and here in black, we're going to see the noise correlation being stacked with some improved convergence with the now famous SVD-based linear filter that some of you may have heard about. And so here, I think this is pretty impressive, because in 8 hours only, we get a pretty good convergence of the waveforms. And we can also, so we've done that between just 2 stations, but we could very well do it also between the virtual source and a line of station. And here that would be the correlogram of our impulsive source when we jump on the ice, and here the noise correlation function. And well, I guess the agreement is clear here. So what do we do with these noise correlation functions? Then we can calculate the dispersion curves. So we move through time distance domain to the frequency wave number domain. And we have 3 components of the waveforms. So on the vertical component, we get flexure motion associated in this dispersion curve. And on the other channels, we get the other 2 modes that can propagate. Right. And I mean, they are quite clear, so there's no ambiguity as to which mode we are looking at to a frequency of about 50 hertz. And with such low frequency, I mean, it's not such low frequency, but we have a model, which model developed in 1998 by Stein et al., that give the dispersion curves in a sort of easy asymptotic relationship. There's no closed form solution, but we can easily derive the velocity of the wave as a function of frequency by solving numerically this small equation, this one. Here you see there is no dependency on the frequency for the 2 modes on the horizontal channels. That's because, as you could see, they are not dispersive, so we can get their phase velocity just by taking the slope of these curves. But the third mode, the flexure mode, you know, it has this shape here. So we needed to solve this equation and to fit a model on it. So our cost function was just, you know, the least square difference between these dispersion curves, the synthetic dispersion curve, and the dispersion curves from the data. And we performed Monte Carlo Markov chain sampling of our solution space, with parameters being the Young's modulus, the density of the ice, Poisson's ratio, and ice thickness. And there's the posterior distribution of our 4 parameters and the covariance between the parameters. And we can see that we have strong covariance between Young's modulus and ice thickness, Young's modulus and density. And there are also parameters that are not correlated at all, such as Poisson's ratio and density here. I mean, the scale here was zoomed into, but here we found, you know, an ice thickness with a resolution of plus when standard deviation was about 3 centimeters. And this we could repeat every day to get an evolution of those parameters. That was the topic of the PhD of Agathe Sthely-Pierre. And here we have 2 directions, so we did that in this direction and in this direction. And this is the curves in blue and red, and we can see the evolution of the ice thickness during the month of March. And why did we have this rise of thickness? Because the temperature was between -20 and -30 degrees, so the ice was growing. At some point it stabilized, and so we didn't have any more increase. The other parameters, on the other hand, are pretty much within the uncertainty range, around 3.5 to 4 gigapascal for Young's modulus, and the density being on average 910 kilogram per cubic meter, which is the expected value for sea ice. For sea ice with salt. And Poisson's ratio is also a typical value for floating ice. So this is the conclusion from this first part. The noise correlation function gave us a very good approximation of the Green's function. And so we could calculate the frequency wave number dispersion curves, invert them to get some parameters of the ice thickness that are useful and missing for sea ice models. You can't do that by satellite. Yes? Yeah, well, we are expecting it to be pretty constant, but we could also very well, include it here, density of the ocean water.
I was just thinking the ice density.
Yeah.
You fix it to whatever number of people have been.
Yeah.
Shouldn't that reduce the uncertainty of some of these?
Yes, of course, but it's of course, if you constrain one parameter, you constrain the others. That's true. But it's for oceanograph, it's very important to get an estimate of the density, so that's why we did. But yeah, of course, yes. Also, amongst the parameters that we could constrain is is Poisson's ratio, because anyway, it's always pretty much in the same range of values. Yeah. So yeah, but to make this of practical interest, you don't want to deploy 250 geophones on sea ice anytime you want to, investigate its properties. So, can we do better? Can we do better with less geophones? And the answer is yes, of course. But how many? What is the minimal number of geophones that with which we can do that? And if you decrease the number of geophones, you can't calculate the frequency wave number dispersion curve. So we have to rely on another strategy. And it was in COVID lockdown, so I was thinking of that, and I got this idea, which proved successful. I had plenty of time to do as many tests as I wanted because I was at home anyway. But first I needed to isolate the ice quakes. And when you have like thousands of ice quakes per day, what do? You use Léonard Seydoux. So you need. So he already showed me some very promising results of what was called at the beginning SCATNet. Now it's SciSnet, okay, and to cluster waveform families, put them into relevant families. And here is the output dendrogram of our data, with some data here being a cluster. The first 7 clusters were ice quakes. I'm not going to comment much of them. So no, not the ice quakes. They happen pretty much all day anyway. But this cluster was quite interesting because we found some waveforms that I would have associated to ice quakes, but are actually anthropogenic related. And here they happen between 6 and 6 in the morning to 6 in the afternoon with a break at lunchtime. And and also these coincidences are always those where there was someone in the field, because there was another group working also for like 2 weeks in the field nearby. So here I looked closer at these waveforms. So by the way, these are examples of families in the clusters. So this would be a cluster associated to ice quakes, and we see here we have plenty of those in these families. icequakes, noisy icequakes, are less with less quality icequakes, and the cluster associated with anthropogenic noise. Here, the colors, I should say, are the three components of the displacement. So yeah, having clusters with icequake waveforms, an icequake, you know, I told you they are dispersive. So you have the high frequency arriving first. So when you perform a time frequency analysis, you have this shape here, or this shape here. And those spectra correspond to a unique combination of propagation distance and ice thickness, given some mechanical properties. So using 3 stations, we should be able to triangulate and find the source, and also invert the ice thickness in the meantime. So this is what we did. So here are some data, some synthetics. The synthetics are not clean because I weighted their spectrum in amplitude with the ones from the data to get better constraint in the inversion. Still MCMC sampling, and the cost function is basically the L2 norm between data and synthetics spectra. I invert for latitude, longitude of the icequake, ice thickness, and also some yes, ice thickness, and also some activation time of the source. No. I do. First arrival, they don't always have it on the. It depends on the processes of the ice cracking, and so we don't always have them. But why do that when when it works with the? So here is the inversion, and we were also able to calibrate the energy released by each icequake because we know how much Pierre weighs. So I won't release this information here, but we also had other experiments in the field where we had this team with they don't do things halfway, you know, they just machine saw an iceberg like the size of the room, and they put ropes, and they did collisions between the ice and this ice flow. So knowing the ice flow weight and the speed, I could calculate the energy at the impact and calibrate that, what I receive here at 5 stations that are in black here. And here the size of the dots are related to the amount of energy that we had. And you see that these icequakes are relocated precisely on the shoreline. And these are tidal icequakes because they are very, so here, these are the sources, artificial sources when we jumped onto the ice and where they made impacts by taking ropes. And so they are correlated with the tide, you know. So these are tidal icequakes. And this is the ice breaks all around, you know, the shoreline, because this is where the tension is. And I was also able even to perform some, you know, power law of the energy released by the icequakes with this nice slope. So it's not the same as for earthquakes, but we are not expecting the same mechanism, so that's cool. And so basically this was related to, icequake were related to cracks about a few centimeters to a bit more than 10 meters. And actually when we were going around here, the moraine, we could see this huge crack going on. So, yes? Yeah, but we are struggling with that. My PhD students have have not converged yet on that. So, but hopefully we'll get there. I agree, because here we have as many rays as not only those 5 stations, but 250. So we should. But anyway, this doing this inversion for thousands of icequake, you know, we have a good training data. So I would like to perform some deep learning analysis and not use GPU time, which is about of the order of several years to invert all my icequakes. So the conclusion for this second part is that icequake can be extracted and classified using, you know, scat size net. We can use the flexural waveform to invert this icequake to get the position of the source, you know, using 3 stations only. We only use the vertical component, but including the horizontal channels. Now we are trying that. We could also constrain Young's modulus. And Poisson's ratio, of course. But the problem is that the main mechanism for these ice quakes here was tidal forcing. And when you're in the open ocean, it's not necessarily that you have more rain around you to get this kind of stress that could release those ice quakes. You would have some ice quakes. I did some analysis on waveforms recorded during campaign on pack ice, drifting pack ice. We had some ice quake, but not as many. So we can forget about tomography with that. It gives you some good idea of some ray path to get some ice thickness around, but not enough to get to make a tomography. So here, a new project started where we tried to combine geophones and DAS and video recordings. And here is an overview of what we started and the first results that we have. So these results arrived like 3 weeks ago, so it's just really brand new. So we went to the St. Lawrence estuary, where we have plenty of fast ice, and we have basically three places where to perform some experiments. And here the idea is really to use what we have learned to characterize sea ice and to understand how it breaks in the marginal ice zone. So we said, okay, let's get an icebreaker and have this icebreaker, go in the St. Lawrence river and accelerate. And so this is an aerial view of an experiment. So here you see the icebreaker generating waves, and those waves propagate in the water, and they reach eventually the ice, and then they start to break it. And depending on the amplitude of the waves, on their wavelength, you can break the ice, further and further away. And so if you get the icebreaker to accelerate, because you know the captain and you want to have fun, then the cone, it's like a cone, because the waves are have more and more amplitude, so they break the ice further away. So we can see very clearly this cone here. Here it was only 30 centimeters. And it was last year, but this year we even did one experiment, it was only 12 centimeters here. Yeah. So here is, And what's very exciting here about what I'm going to show you is that we had drone recording this wave propagation. And it started without me asking. Funny. And so from this recording, we can convert with some geometry, fancy geometry, what happens in the plane here, and convert it into a vertical displacement. And this led to this map here of displacement, where you see the wave here propagating, and here this is the field that we've recorded. And we can have a sensitivity of 2 millimeters on the vertical displacement. And as you see, the ice is breaking here, you get the field being propagated. So out of that, we can extract the waveforms. And this is what they look like for the two drones, okay? And for a buoy here that was looking at the amplitude straight on the ice. So we have pretty good agreement, except here in this part when we start to have this offset. And that's because the ice is broken, so there is some horizontal motion that also translates in the vertical plane. But this we are going to fix by using stereo imaging from our recordings. And I kind of find that fascinating, because if you have the fluctual wave displacement in every pixel of the image, I'll leave you to imagine what we can do in terms of tomography in correlations, Yeah, it's actually there's a transition between gravity wave in the ice and gravity and fluctual wave in the ice. So there's this transition that we observe also. So I get to that. But here, just a few words. Even if we have a triangle points and we have a very directional source, which is the swell, how do you get the dispersion curves or stuff? What do you do with that? Well, this guy is very intelligent here, Antonin Eddy. He worked out, some kind of noise correlation-like processing where he can extract the phase from the noise. Here it was really noise. He can extract the phase. This was not the swells from the boat. It was actual noise, you know. So extracted the phases with some geometry. He likes geometry. It's the same guy who converted this image into this one. He converted that into some wave number and fitted dispersion curve. This dispersion curve with the model gives the ice thickness very accurately. By the way, really, we drilled the ice and we are accurate to almost the centimeter in terms of thickness. So, yeah, so this is all we have for now in terms of processing of the field data. But we are also working on laboratory analysis. So here, there's a fracture of a brittle thin sheet made of lacquer. So they vaporize lacquer. It kind of consolidate. And here, let me show you. This one. I wanted to show this one first. So here, this is the camera recording. And from this camera, we are able to extract the displacement field very easily and convert that into a dispersion curve, just like we did previously. And here we see this, actually, to answer your question, the dispersion relation of the incident wave, you know, circles. It shows the transition between gravity waves here and flexural wave. So it depends on the frequency, of course. And then I just repeat this one. If you increase the amplitude of the incident wave, you will break the lacquer, okay? And so it gives you some kind of threshold in terms of amplitude of the incident wave, in terms of wavelength of the incident wave, above which you are breaking the material. So we extract now, we want to extract this threshold on sea ice and fit that. So we already have a few points on this diagram, thanks to previous experiment. And so, of course, for that you need Young's modulus, you need the thickness, you need but yes, we get that already. So, and then we can feed that to some sea ice model. The new sea ice models being developed, and there are many being at the moment. Yeah, so I'm going to conclude now. So I hope I have convinced you that passive seismology is useful for monitoring sea ice and ice thickness and elastic constants, because these parameters are essential for sea ice models and further for climate models. Of course, they can also be measured quickly in the field from active sources. I mean, you just have to use a hammer, deploy 16 nodes. We've done that many times. It takes about 1 hour. And so it's possible to extract seismic. Also, it's possible to extract seismic waveform from the recording of ice well and identify threshold breakup due to geophysical forcing. So in terms of future works, of course, we are one step away to achieve passive sea ice thickness tomography from video recording, which would be a major breakthrough, really. I mean, imagine doing noise seismology, interferometry with video recordings would be great. And this summer, at the end of the summer, in September, we are, not me, but the PhD student is going on the icebreaker Amundsen, go straight up the Nares Strait and end up in the Lincoln Sea to perform these experiments with drone and seismic experiments straight on pack ice. So yeah, it should provide us with very rare kind of data. Also, we have planned to use DAS. You know, we've not left this aside, obviously. So we've done some experiments on mountain frozen ice, on a frozen mountain here in the French Alps. Okay, we've deployed the optic fiber cable along, and so this is the kind of recordings that we get, that we can zoom on some parts of this recording and get the quasi-short mode, also the quasi S0 mode, which we can invert to get ice thickness and Young's modulus. It was successful, so we are very confident that's going to work. And now the next step is to use that and transfer it on CIs. We are not able to do it this year because the DAS was on the Astrolab. And it arrived only 3 days too late before we can take it with us for the new campaign. But next year, surely we'll do that. All right. Before I conclude, I would like to thank you. And also, I'm looking for a postdoc to who is expert in deep learning, to process our data and replace those kind of heavy inversions using a model with just a neural network. And that's it.